Hello everyone, and we are going to be starting 3.0 Introduction to Energy. So if you haven't read the chapter in Coletta, please do so. That'll be chapter 7. If you are in Physics 111, please begin homework number 9. Physics 121, please begin homework 6. And this is related to lab 8 and 9. So we are going to be doing a few things here. We're going to first of all learn what is energy and the different types of energy, mechanical energy as well as non-conserved energy. We're going to learn how energy is transformed and transformed, the conservation of energy law, and also what is power. All right, so energy, in essence, is what is everything, I suppose. It's the best way to say it. It's everything in the universe. Okay, it's what gives things motion. It's what everything. It's the interaction of everything that has matter, but also everything that doesn't have matter as well. So, for example, photons don't have a mass, but they do have energy, okay? It's how things are transferred, how energy is transferred from one object to another. Basically, it's what gives everything force and consequently motion, okay? So, one of the things that we have to learn is that the main property of energy is that it enables it to do work, right? And work has a very specific definition in physics, okay? And that later on, this work and this energy and also transfer of energy can be turned into heat and actually leave the system that we're looking at. So, in essence, energy is everything, okay? And it's what gives objects force. It's what applies a force to something and then later on gives it acceleration and velocity and movement. So one of the things that we have to do is learn what is known as the basic energy model is. Okay, so if you have a confined system right here, and we'll get more into this later. This is just a summary of what we're about to do. So you have a confined system of kinetic energy, potential energy, chemical energy, thermal energy, all the different forms of energy. If you put work into the system, you will get work out, right? So if you put heat and work into the system, heat and work will leave this system, okay? And so what is work? Well, in essence, work is a force times a change in distance, okay? So work is, like I said earlier, work has a very specific definition of physics. Work is a force applied to an object over a specific distance. So, for example, pushing a car a distance to the right, as long as your hands are touching the car, and you are pushing it a distance, well, then work is being done on that car. Okay, and that is called work. And energy and work have the same SI unit, has the same unit, which is joules. And 1 joule is a Newton meter. And so some of you have probably taken chemistry. So a joule and a calorie are related. And also, if you've looked at the side of a cereal box, for example, you'll see how many calories this food is, right? So what they're really talking about is energy, right? How much energy is that food? And so 1 joule is 0.239 lowercase calories. But what is written on a side of a food carton is kilocalories. So that is 1 joule is 0.00000 239 kilocalories. All right. And I should probably write that down. So the unit, you know what? I'm going to need to have use comments and push this back again. And now I could write. So what I was talking about is 1 joule, which is the unit of measure for energy and work, is 0.239 lowercase calories, right? But if you're talking about food, 3239 kilocalories, which is uppercase calories, okay? Which is also like saying capital K, lowercase k and calories, right? That's what a kilocalorie is, right? So suffice it to say, how do you get force times a distance, right? Or force times a change in the distance? Well, for you Physics 121 students, what you're supposed to do is integrate force across a distance, okay? So you integrate force with respect to a distance, okay, from some initial to some final limit. And what you basically get is this, right? And so that's how work and energy is related to force, right? In that the definition of work is force times a change in distance, okay? And what you have to keep in mind is that while energy and work, they are scalar quantities, right? It doesn't matter where you begin or where you end when you're doing that stuff, but force and displacement, right, which this delta S here is a displacement vector, are vectors, right? So it is possible to do negative work, okay? And I think we'll talk about that. And we'll talk about that, how work can actually be a negative thing, and in more detail. But suffice it to say, if this force is in the same direction as the displacement vector, then that becomes a positive work. But if the displacement vector is to the right and you have a force to the left, force vector to the left, then that is negative work. So it's weird, kind of, is that you could have work added to a system or work being taken out of a system. That's kind of like saying you're adding energy to a system or taking energy away, okay? Heating something up or cooling it down. So work and heat, and we'll get more into later on what is heat, but work is the transfer. It is actually the mechanism to transfer energy from one system to another, okay? And there is a relationship of work to kinetic energy and work to potential energy. Basically, how work is related to these mechanical energies. So work is what is being exchanged between energies, right? So you have kinetic energy, you have potential energy due to gravity. What is being transferred between those two is work. So work is what transfers between systems, okay, or two energies, right? For example, we have a pitcher. He's applying a force to a ball, so the force is so the ball's moving to the right, so it's got a displacement vector to the right, and the force vectors to the right as well. When the ball then is let go from his hands, that work is now been changed to kinetic energy or energy of movement. Okay? So in a little bit, we are going to be getting in how these vector sums of forces are going to be related to overall net work, okay, which causes a particle's energy to change from one thing to another, okay? So let's do some little activity-based things right now, and talk about what the definition of work is, and I'm going to write it right here. And I'm going to do a better job at writing it. Work is going to be equal to force times a displacement. Okay? And I just put a regular D, a change in D, that's the displacement. And I use D in terms of it could be moving to the right, it could be moving to the left, so X direction or Y direction. So you'd put X, sigma, delta X or delta Y here. So let's try to get you guys to interact with this. So there are two ways at which, there are two things that could cause work to increase or decrease. And that one of those is by increasing or decreasing the force. So if you notice right here, the force right here, if that goes up, that work goes up, right? And since this is a numerator and this is a numerator, they're directly proportional to each other. So if this goes up by 1, this will have to go up by 1 in order to keep the displacement constant. Okay? If it goes down, the force goes down, then work has to go down. Okay? Another thing that you could do, if you keep force, if you want to increase distance, displacement while keeping the force constant, right? So you're pushing a ball and you're pushing it 2 meters, now you're pushing it 3 meters. Well, that's going to cause, applying the same force over longer displacement is going to also increase the amount of work, right? So, for example, if you increase, so if you take a load of, so you take a load and you take it from, you bring it to 1 story, that's going to cause a certain amount of work, but bringing the load from the bottom to the very top, 2 stories, is going to be twice the amount of work it's going to take. So the amount of force that you're applying is constant, but the amount of distance that you're raising it is increasing right here, right? Okay. Another way it could be looking at is if you take a load, and I'll just draw this little bag right here. You have a little bag right here. You take it from the bottom story to the top story. Well, that's going to cause a certain amount of, you're going to have to use a certain amount of energy to do that, right? A certain amount of joules or calories. Well, now you take 2 loads and bring it up 2 stories. That's going to be twice the amount of calories, right? So there's this direct relationship between, and I'll remove these arrows really quick. There's a direct relationship between force applied, more force, more work, and also displacement. Moving the same force, a larger displacement is going to account for more energy. You're going to need more energy to do that, okay, or more joules. Another thing that you have to keep into mind, that since force is a vector and displacement is a vector, if these two vectors are not parallel to each other, then that force vector won't be related to the displacement. Okay, so for example, let's say you need to move an object. You are applying a perpendicular force to an object right here, but the displacement, the object was being moved to the right. Well, that is going to account for, so this is 90. Well, that is going to be, actually, let's get rid of that and turn this to black. So you have to keep in mind the relationship of these two vectors to each other. A force vector has to be parallel to the displacement vector, or a component of the force vector has to be parallel to the displacement vector, right? So suppose you had a force vector pointed up and to the right. Well, it has a displacement vector upwards. Well, displacement vector upwards. It has a vertical vector component, and it also has horizontal vector component, right? Well, the vertical vector component won't contribute to the displacement at all, right? And so this relationship, this is a dot product in between these two guys, right? And so that vertical force is at a 90-degree angle to the displacement vector, right? And so what that means is that force times the distance, and that parallel force parallel, is at a 90-degree angle, and that is not going to contribute to the displacement at all. Okay? So not only can work be positive or negative, but the angle of that work is going to be important too. Notice that the parallel component, this is the perpendicular component, notice that only the parallel component contributes, the parallel component, meaning parallel to the displacement, contributes to the work, right? So this force vector, only this component of the original force that's off at an angle contributes to the displacement. The perpendicular part does not contribute to that displacement in any way whatsoever. Okay, so when calculating work, you have to keep in mind that this is a dot product between the displacement vector and that, right? Which is going to mean this, is that displacement vector and that force vector have to be parallel to each other. And it kind of makes sense, right? If you need to do energy on something, right? If you want to move something, you want to move it to the right, and you start pushing it up, well, now the displacement vector is not going in the displacement vector, right? So you'll be doing, hopefully, if you're pushing an object up and it does actually move up and down, well, now that perpendicular, that vector, that up and down part of the force is going to contribute to the displacement, right? So it's basically whatever component of the force that contributes to the displacement vector is what is actually doing the actual work in transferring it from one energy to another. Okay, so there are two types of mechanical energy. There are two forms of it. One is called potential energy, and another one is called kinetic energy. All right, and you may have heard of this, and you also probably have your own definitions of this. It's probably been used before around you, but just to make sure that we all understand what it is that we're working with here. is that in physics, potential energy and kinetic energy have very specific meanings and quantifiable meanings, okay? So let's start off with kinetic energy, okay? So to just basically sum this up, there is a direct relationship between work and kinetic energy, okay? And this is also known as the work energy theorem, okay? And basically, what we had learned just a moment ago is that work is equal to force times a change in distance, displacement, right? And also we have to consider the angle too. Well, this is going to eventually be turned into what is known as kinetic energy, right? So work can add to kinetic energy, right? So you have a box on the ground and you begin pushing it. It's very slick ground, and you give that box a shove. So the length of your arms is the displacement vector, and the force of your push is the force. And hopefully your arms are perfectly parallel to the displacement vector, and that'll maximize the amount of work that you give it, right? Well, when now that box leaves your hands, it's now going to start speeding up, which means you've added energy to it, right? The work that you've done has added energy to something, right? Well, your friend is a couple feet away from you, and now the box is flying towards your friend. So basically, you've provided a force across a displacement. This is the length of your arms, right? So this is you standing here, and you've pushed a box or thrown a ball, and this is the length of your arms. You've got really long arms. Okay. Well, now this ball has got a motion, right? So now it's got a kinetic energy, right? So you've done positive work, right? You've added kinetic energy to something, to this ball. Now over here, your friend is going to catch the ball. So the ball's still moving to a right, a displacement, right? And this is the size of your friend's arms. So he's got really long arms too. Super creepy picture. And now your friend is gonna, the force vector is to the left, the displacement vector is to the right, right? Well, now your friend and the ball's got kinetic energy, it's going to come to your friend. And your friend has to slow it to a stop, right? So that is what your friend is now taking kinetic energy out of the system and is doing, and thus that is called negative work, right? So positive work speeds up something. Negative work will slow it down. It's kind of like saying that. And anytime your initial energy is greater than your final energy, that is going to be slowing it down, right? Since work is equal to the change in your kinetic energy, right? If your initial kinetic energy is greater than your final energy, this will be, right? This will be, I'm going to actually write a really large K here, right? Your initial kinetic energy is greater than your final kinetic energy. Well, that will be a negative delta K, which is going to result in negative work, right? If your kinetic energy final is greater than your kinetic energy initial, well, that is going to be a positive delta K, which is going to have to come from a positive work, right? And so that's basically the relationship of work to energy. You apply a force to an object, well, and that object begins to speed up, you've increased the kinetic energy of the object by doing positive work, right? Well, now when you are applying a force opposite the direction it's moving, well, you're then going to be slowing down that object, right? And then that is going to take out the kinetic energy of the system. And so this is the work energy theorem, okay? And this is basically the main concept of this, right? There is a mathematical form of this, and it takes into account all of the energies, right? So the entire energy of the system is equal to the work done or taken out of the system, right? So you add up all the energies of the systems, all these different types of energies, which we're going to learn later on, and all of the change in those energies, you add it up, and that should be the amount of work taken out or added to the system, right? Okay, and so there's a lot of different types of energy transfers that could happen. So work can go to kinetic energy. Later on, we're going to find out work can go to thermal energy, like, for example, friction. When the box is sliding across a rough floor, the frictional force is going to be heating up the object, right? If you put your hand on a table and you rub it back and forth on the table a lot, well, your hand is going to start heating up, right? So the force of your muscles pushing your hand back and forth is going to change that work to thermal energy, right? And that is going to then be taken out of the system. There is a type of work transfer where your force in pulling back a spring is going to make the spring start to coil and store that energy. And so this is potential energy, which is U sub S. That S is a spring, right? So that S refers to a spring. And thermal energy is heat, which is Q, or heat, right? And so one of the things that we can say is that kinetic energy is the energy of movement, right? Anything that is moving has kinetic energy, okay? Now, how we measure work is by the change in that kinetic energy, the work done. But really, if you just take a snapshot of an object at that moment, if it's moving, it's got kinetic energy. Now, I don't know if that's the initial kinetic energy or the final kinetic energy, so that I could get the change in the kinetic energy. And then after that, I could talk about the type of work done. But suffice it to say that kinetic energy is the energy of movement. Okay? Well, some of you in physics 121 and also 111 may want to know how, what's the relationship of force to kinetic energy now, right? So what is kinetic energy in an equation form? And how is kinetic energy, we said, is related to movement? How is it related to movement? Well, kinetic energy, which is equal to work, is equal to force times the displacement, right? So I'm going to just go ahead and make that relationship right here. And so delta K, which is kinetic energy, energy of movement, is equal to force times a displacement, right? And what we had learned earlier is that Newton's second law, force is equal to mass times acceleration, right? And just to make this cleaner, I'm going to move it down. I'm going to, now mass is a constant. And so what we're going to be integrating is acceleration, right? with relationship to this is the acceleration, and with respect to the distance or displacement. And what we could say here is, continuing with this integral, I'm going to keep the m in front, is that A is also known as dv dt, and this is ds, right? Well, if you recall back to calculus, there's a really cool little trick that we could do with this. So delta k again. I'm going to keep m to the front, so I'm going to bring this whole thing, so I'm going to rewrite this whole thing with our cool calculus trick, in that I'm going to just rearrange that formula. dv ds over dt times ds. And I'm just going to check to make sure this is still just dv dt ds, right? So ds crosses out ds, so that makes dv over dt, and then we have a ds left over. Okay, cool. Okay, so this is s. Well, ds over dt, that's distance divided by time. Well, isn't that just velocity, right? ds velocity ds. And so I'm going to rearrange this formula and bring the velocity out in front, and dv ds times ds, right? Well, look at this. We have velocity dv over ds. So the ds's can cancel out, right? So delta k is going to be equal to m integral v dv. And so now I'm going to actually put on my limits. And so what we could say here is that if we integrate from initial velocity to final velocity of this velocity right here, this component velocity, with respect to velocity, what you get is mv squared divided by 2 from vi to vf. And so I'm going to plug in this. So mvf squared over 2. I just plugged in the top part. Now I'm going to plug in the bottom limit. mvi squared over 2. What that comes up with is that kinetic energy is 1/2, the change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared, right? So that's kind of a big deal, because there we've actually, through derivation, through derivation, I don't need to do that. So this right here, I'm just going to underline it. There we go. Through derivation, we have actually defined what kinetic energy is, using work and thus using force to do it. Okay. There is another way to do this, and this is for 112 students, right? It's really quick. So you learn from motion that velocity final, this is one of the equations of motion, velocity initial, v final squared plus equals v initial squared minus, plus 2a delta times the 2a times 2 times the acceleration times the displacement, right? And so what you could say is that V final squared minus V initial squared. I'm going to just bring that to both sides, is equal to 2A delta S. And so dividing both sides by 2, you could say V final squared minus V initial squared divided by 2 is equal to A delta S, right? Well, kinetic energy, which is equal to work, is equal to F dot delta S, right? And F is mass times acceleration times delta S, right? So acceleration delta S, which we just learned is this, is equal to mass times V final squared minus V initial squared divided by 2. All right, and multiplying that all out, we get the same thing. So there's two ways to do this. If you're in 121, it will be this, and if you're in 111, it will be this way, right? And you get, in both ways are valid, right? Just using different tricks. And there you go. All right, let's move on. I'm going to save that. That looked pretty cool. So now we have, on the next slide, we have an actual definition of what kinetic energy is, right? It's direct relationship to work and force, okay? And so force times distance can, if it's just not displacement times an actual, a force times an actual position, can actually have a kinetic energy associated with it, okay? And basically, here is the entire thing right here. What we have just found mathematically is that, and also conceptually using work, is that kinetic energy is the energy of motion. All right, and there's some interesting things here about this equation. Okay, and I'm going to write it just basically right here. In that kinetic energy, which I'm just going to call K now, not KE, is 1/2 mv squared. So let's talk about the proportion of velocity to kinetic energy. All right, because it is directly proportional, right? But it's got this multiple to it, right? Since kinetic energy and velocity are both on the numerator side, you have to take in, there would be, if one goes up, the other one would go up, right? But the fact that velocity is being squared is going to kind of add a level of thinking that you have to do when you say that if the velocity goes up, how much will the kinetic energy go up? So for example, let's do this. Let's say your velocity increases. It increases just by, let's say your velocity doubles, right? So if your velocity doubles, right, well, we're going to be squaring that. That means it's actually 1/2 mv squared. Let's say your velocity, compare one velocity to two velocity. Well, the kinetic energy of one velocity is just going to be equal to 1/2 m times 1v squared, right? Which is just 1/2 mv squared. But if your velocity gets doubled, well, the consequence of that is that your kinetic energy is going to quadruple, because 2v squared is going to be 4v, which is going to actually work out to be 4 times 1/2 mv squared. So if if your velocity just goes up a little bit, it's going to drastically increase your kinetic energy, right? Which means, by the way, that whatever is going to slow you down is going to have to now work a lot more, okay, to slow you down. So the fact that this velocity square is being squared, you have to really pay attention to that when you're kind of thinking about, kinetic energy, okay? Good news is that mass is still just directly proportional to kinetic energy. So if mass goes up by 1, then kinetic energy will go up by 1. Again, if mass goes up by 1, then kinetic energy will go up 1 unit, right? So if your mass increases from 1 kilogram to 2 kilograms, well, your kinetic energy is going to now increase from, for example, 1 joule to 2 joules, right? Anyways. So they're directly proportional to each other, and incrementally proportional to each other. While velocity is directly proportional to kinetic energy, but is not incrementally proportional, right? It's got that square, and you have to keep that in your thought process. Okay. So let's do a little bit of a problem. So suppose you have a car that moves. You have 2 identical cars, meaning they have the same mass. So you have 2 identical objects with the same mass. One car, this car at the top, is going 4 times faster than the identical car down here. Compare the 2 kinetic energies. Compare the kinetic energy of the identical car to the very fast 4 times the velocity of the other car. How much more will the kinetic energy of the speedy car be in comparison to that? Will it be 4 times the kinetic energy, 8 times the kinetic energy, 12 times the kinetic energy, and 16 times the kinetic energy? So think about a moment, hit pause, and use the kinetic energy equation, 1/2 mv squared, to do this. Okay? Hit pause now. All right, let's try it out. So I'm going to do a little bit of a drawing here. And let's try it. So let's do this car, the slow car. The slow car, let's just say it's going at, let's say it's got a mass m, and let's just say it's going 1 meter per second squared, or just like 1 velocity, right? It's going 1 velocity unit, and that's being squared. What that means is its kinetic energy can look like this, and that's the kinetic energy of the slow car. Slow, okay? Well, the speedy car, it's got the same mass, but it's going 4 times the velocity of the slow car, which means that 4 v squared, so I'm going to just write this out exactly as I've done it, is going to be 16 v squared, which I'm going to bring the 16 to the front and the 1/2 mv squared to the back. So what this could be is saying is that this speedy car is going 16 times the slow car, right? If the slow car is 1/2 mv squared, it's got 16 times the slow car's kinetic energy. And this is this whole thing is the kinetic energy of the speedy car, right? So that's the kind of crux in quantifying and analyzing the units and the variables of kinetic energy, okay? is that it's that velocity being squared is kind of problematic. Okay, so hopefully this helped you out. One thing that we need to learn to do is that you can use graphs to figure out kinetic energy, right? The change in kinetic energy, right? So we've learned before that delta K is equal to work, right? And that work is equal to F dot. In this case, it looks like a horizontal displacement. So the dot product of F delta X, right? And so what we learned is that when we integrated force delta X, that right there basically tells me that the area under a curve of force versus displacement in the x direction is the work, right? What that means is this entire area right here, I got a little crazy with some of those, so this entire area right here, this entire triangle this area right here is the work done, right? And so we could do cool things if we have a graph of force versus displacement, right? The displacement here would be 200 meters to 0 meters, and the force would go 5,000 to 0, right? So at a 0 displacement, you're applying a force of 5,000, right? But the further to the displacement, the less force you're applying until finally it left your hands, right? Or left whatever was causing it 200 meters away, right? So the area of this is this, right? So you could do this a lot of ways, and in Physics 121, you would create a prediction equation and then integrate that prediction equation versus across the displacement, right? And so what you could say is the final force is equal to the initial force, and so this is going across this. Rather, I should more say it like this. It's this object has whatever's causing this. It's a car. Oh, it is a car. Okay. We're going to create a force prediction equation, right? And then integrate this. And it's just a linear line. It's just a line. So it's just a linear prediction equation. Well, we're going to create a prediction equation, right? So we're going to try to predict a y equation. Well, that's equal to mx plus b, right? Just like we learned before. But in this case, we're trying to predict a force equation, right? And this m is a slope. X would be actually in this case is x, right? So this is the slope. M is the slope. X is the variable x, distance, and b is going to be the y-intercept, right? Well, let's create this equation. So in order to do this, we need to find the slope. Well, the slope here is going to be rise over run. So it's going to be delta F over delta X, right? Which is going to be 5,000 newtons minus, and I'm going to need some room here. I'm going to erase this stuff. Actually, I'm going to move all this stuff down. Right, so the slope of this line is going to be equal to delta F over delta X, rise over run, which is going to be 5,000 newtons, and it ends at 0 newtons, over 200 meters is a final, minus 0 meters, right? So this is going to be 5,000 newtons divided by 200 newtons. Shoot, that should be meters. And so the slope here is going to be 5 over 2 Newton per meter, right? So this is going to be 5 over 2 Newton meters times X plus the initial force, which is the y-intercept, is 5,000 newtons, right? So we just created a force equation, right? So in order to do this, what you do is you integrate this from the initial, and so we're integrating with respect to x, so we're going to integrate from 200 meters, from 0 meters to 200 meters of this entire equation, right? 5 halves newtons per meter, x plus 5,000 newtons dx. And that should be an x. There you go, right? If you are in 112, and this is probably the smarter thing, is just get the area of a triangle, right? So the area under the curve in this case is going to be the area of a triangle, right? So area of a triangle. And so the area of a triangle is going to be 1/2 the base times the height, right? So it's going to be 1/2 5,000 newtons times 200 meters, right? So, oh my goodness, this is a lot of energy. So 5,000 newtons times 200 meters divided by 2. So this is going to be 5,000 times 100, which is going to work out to be 500,000 joules, right? In integrating this, it'll work out to be 500,000, right? So walking through this, you know, if and you could see they did the exact same thing here. So they chose to just, you know, chunk the work. They didn't go ahead and then integrate that that equation from 0 meters to 200 meters, and that was 5 halves Newton meter plus 5,000 meters dx. What they did is just say, oh, well, this is just an area of a triangle. Rather than do all this, let's just go ahead and get an area of a triangle. Super easy that way, right? Well, once you have that done, and we have work now, the work needed to speed up a car, and that's going to be roughly 5 times 10 to the 5 joules, right? Well, now we know that that's equal to delta K, right? And so this 500,000, oops, I should just put 5 times 10 to the 5th. It's a little bit cleaner. 5 10 to the 5th joules. Well, that's equal to 1/2 MV final minus 1/2 mv initial, right? But in the problem that they stated, the object started from rest. So that means, actually, I should be a little bit more concise in that the initial velocity is 0 meters. And so what you have is this 5 times 10 to the 9th, or 5 times 10 to the 5th joules is equal to 1/2 mv final squared. And so that's how they get this part, right? They solve it for the final velocity, and they find out that it's 26 meters per second, okay? So when you're doing these problems, try to do the simplest thing that you can do to get towards the answer, right? And in this case, this is a pain in the butt to do, really, right? So this is 5/2 x. Whoops, I forgot x. That's important. 5/2 x, right? So this would be 5/4 x squared plus 5,000, and then you'd have to plug in 200 meters on top of that, and it does work out to be the same number as 5 times 10 to the 5th joules. Or you could just get the area under the curve like they did here, the area of a triangle. So it's really up to you how you want to do this. Some people, it's easier to create a prediction equation and then integrate it. For 111 students, think in terms of shapes, triangles, squares, that kind of stuff. Those will be the type of problems that you're going to be given. Okay. So moving on, the other type of mechanical energy that we're talking about is potential energy. All right, and in physics, potential has its own very specific definition, right? And just like in other terms, you could say that it's got stored energy. That an analogy between potential is stored energy. And there are many things that can store energy in life. A rubber band can store energy. If you pull a rubber band, you're pulling it and you're stretching it, right? And now it's fully stretched. That energy is ready to go. It's ready to spring back and snap at something and release, right? So a rubber band, a spring, they all have this stored energy. Well, in a weird way, so does water. If you bring water up to a height, well, now that energy is waiting to go and flow downhill, right? So you could say that if you lift any mass up a height, well, now you've created work and you've added a height to something, and now that mass is just waiting to fall to the ground, okay? So there are two types of potential energies or stored energies in physics. One of them is in reference to the Earth, which would be potential energy due to gravity, and another one is a potential energy due to a spring. The spring part we're going to talk about later on. So we just want to talk about potential energy due to gravity right now, okay? And the definition of potential energy due to gravity is that potential energy, it has a very specific definition. So I'm going to go ahead and write that here. Potential energy, some textbooks write it with a PE. That's the same thing as using a U, okay? And since it's U due to gravity, we're going to put U sub G. Okay, and that's the potential energy due to gravity. Well, potential energy due to gravity, just straight to the point, is the force of the weight, or it's the weight of the object times the height that it's been raised to. Okay, so potential energy due to gravity is equal to mgh, right? So you've raised it to a height. It's the only type of mechanical energy that is due to a position, right? So if you lift an object up, you're lifting it to a positive y position. So this, you could actually call this the energy of position in a way. I like to call it the energy of height. Okay, any object that is a height up above the ground has some stored energy, and the earth is going to pull that weight down from that height. Okay, so we're kind of working with a little bit of some equations right there, but the strict definition of potential energy in relationship to the work energy theorem, you could actually say is this, is that for you to raise something up a height h, you could actually say this, is that delta U is equal to work as well. Well, negative delta U is equal to work as well. We'll talk about why there's a negative in front of that. Okay. So negative delta U. So let's talk about this. So we have negative delta U, right? And we're going to talk about raising a ball from an initial height down here, a distance 0 meters, to a final height. Actually, hold on. We want to talk about it going from a final height to an initial height of, say, 8 meters up, which will be the initial height. And this sucker's got to be speeding up. So that means this is the Earth is going to cause a down vector, pulling it down. And so its displacement is going to be in the delta y direction. And I should give myself more room. So we're talking about the Earth's force acting on this. And the Earth is going to be pulling an object down. And its displacement vector is going to be down, right? So it's going to be going from a higher height, for example, 8 meters up, to a lower height, way down here at 0 meters down, right? Which is weird because our y final is actually lower than y initial. It's going to, essentially what that is saying is this: our initial height, which is y initial, is going to be a higher number than our final height, okay? And so the object, the force that the Earth is pulling on this object is mg. It's the weight of the object, okay? And this thing is being displaced, a displacement in the y direction. Okay, so when we're integrating this, y initial to y final, this is going to be mg delta y. Actually, I'll just go ahead and integrate it for you. It's going to be mg y from y initial to y final, right? And so negative delta U is going to be mg y final minus y initial. Oops, that should be mg y initial. So the Earth is going to be pulling this from a higher height, So it's going to end up on the ground. Than this, right? This is 8 meters up. So the interesting thing is the Earth is doing work to pull this thing down, which is then creating this potential energy into kinetic energy, right? Right? It's adding kinetic energy in this and speeding it up. And so the only way this can happen is if you say this, is that the delta y, the delta u, which is y final, which is y initial, has to be a negative number. You have to make that a negative number for it to add kinetic energy to this, right? And that's the reason why this is a negative display, a negative delta u. Okay? So to sum up, the work, this is not the work potential energy theorem, it's just how work is related to potential energy. So work is equal to negative delta U. Okay. So work is equal to negative delta U, and that's what this is saying right here, right? But in order for there to be gravitational potential energy in this particular case, okay, and I should erase this right here. Whoops. In order for there to gravity to be doing work on something, the force of the Earth pulling down on the object has to be in the same direction as its change in displacement. Therefore, if it has to start from a height up here to a lower height. And when that's the case, this mg y final is lower than the initial height, right? Which means y initial, if it's y final, is going to be a lower height than y initial, and that is how the change in energy, what you would end up finding is that this is going to work out to be a negative delta U. Okay? And so that's how you end up with work being equal to negative delta U, but also equal to delta K. So which is going to require more work? To require a greater change in gravitational potential energy. Lifting a 50 kilogram sack up 2 meters, or lifting a 25 kilogram sack up to 4 meters? Or will they require the same amount of change in potential energy? So go ahead and pause the video and try to answer this question. Okay? All right, let's go ahead and try this out. So I'm going to go ahead and start drawing. And let's go ahead and to answer this question, figure out the potential energy due to gravity, the change in potential energy due to gravity for this object. So right here, potential energy due to gravity, we know is going to be mg delta y. And that's delta U sub g, which in this case is going to be 50 kilograms. And we'll just use 10 meters per second squared for gravity. So that right there is the force of weight of the 50 kilogram object. And its change in potential energy is going to be, it ends up at 2 meters up, and it started at 0 meters, right? So this is going to be 1,000 joules, or Newton meters, right? A Newton, again, is a kilogram meter per second squared, so that's a Newton, and then multiplied by this, so again, a joule is a Newton meter, all right? let's do the potential energy due to gravity for the 25 kilogram object. Well, that is going to be 25 kilograms times 10 meters per second squared. Again, we're just using that simply to be that. And this is going to be 4 meters minus 0 meters, right? So this is going to be 250 newtons times 4, which is actually going to work out, again, to be 1,000 joules. So the answer is they both require the same. So this is an interesting problem because you have to really think about what is potential energy and what is work. So what is potential energy due to gravity and what is work? So here's the problem. Rank from largest amount to smallest amount, the amount of work needed to lift a 20 kilogram ball in each case. So in all cases, the ball is being lifted from the point on the ground to a height of 3 meters here. This is also going to be 3. It's a 3, 4, 5 right triangle. And in this case, you're bringing it up a step. You could drop it there and take a rest, bring it up a step and drop it there until you get it to a height of 3 meters. So, or are all they the same amount of work needed? Well, let's look at this case. You're going to be lifting it from this point straight up to 3 meters. No breaks, anything like that. If you're pushing this up the ramp, at least you could put it against your feet and let it rest for a little while. And then maybe a moment later, push a little bit more and push a little bit more. In this case, you just have to lift it 1 meter, put the ball there. You could crawl on top of it maybe, or just actually maybe you could just lift it. It's only 3 meters, so stand here to the side. Take a break, let it sit there, lift it a little bit more, 1 more meter, take another break, and then lift it to last, and you're at the top. So this problem illustrates what the difference is between effort and the physics definition of work. A lot of us think work is effort. So think about it. Go ahead and pause the video and select your answer. All right. Well, in the last chapter, we learned that work is equal to force times a displacement. Okay. I don't know why that's a window popped up. Force times a displacement, right? And we also learned that work is equal to negative delta U sub G, which is this would be the work due to the Earth, right? So what I'm going to do, I'm going to actually erase that. We're going to just concentrate on your work, which is the weight of this object. So you're going to need to lift the weight of this object up a distance delta y. Okay? So this is the amount of work you have to do, not the work due to gravitational potential energy. This is how much work the Earth is doing. This is how much work you are doing, okay, in lifting this ball up to here. Okay? So the ball would be, this ball, you're applying a force upwards and it's being displaced in the same direction. So that's the reason why we are using this definition of work and not this. In the case of this, the Earth is pulling down on the object and then it is displaced being in the downward direction. So that is the Earth pulling on the object. This is us pushing an object up. Okay? And so if you notice from this equation, and also just the general definition of work, it doesn't matter really the path that you take, right? So it just matters, since this is a delta y here, that's what makes it a scalar problem. It's the weight of the object's ending spot minus the weight of the object's beginning spot, right? So you have a weight of the object starting here at the bottom, and then it ends up at the top. It doesn't matter the path that you take. It just matters, the only thing that would matter as far as this weight of this object, which is the force in this case, is if this vector matches up with this vector, right? But we're assuming the displacement vector is going to be in the same direction as the force all the time. So anyways, here we go. So it just begins here and ends here. Well, this problem, it begins here and ends here, also a height of 3 meters. This one begins here. You take little breaks, yeah, you do, but it still ends up finally in the end here. So really, all of these cases require the same amount of work because it's just the beginning and the end. It doesn't matter what happens in between or how much time it takes. This equation doesn't take into account time or any of that stuff, right? It's just the beginning place, the beginning, and the end. Okay? Which kind of brings me, we've kind of been talking about this the entire time, about deciding if you're putting work into a system or is work being out of the system. So in this last problem, if you noticed, work due to the Earth is a negative U sub g. But in this case, it's still like the same type of equation. Look at it. It's mg delta y. But notice that we don't have a negative in front of this, right? So it all depends on the direction of the force vector and direction of the displacement vector, okay? Okay, so you have to kind of think about that, right? So if the direction of the force vector is in the same direction as the displacement vector, okay, that would be positive work, right? And that's what we're talking about right here. If the force vector is opposite the direction of the displacement vector, if the force vector is opposite the direction of the displacement vector, and I'm going to put a little delta y, this top one is positive work, this bottom one is negative work, right? So it's kind of weird in the Earth's case, in our case, when we're lifting an object up, if you're doing a pull-up, you're starting here at the bottom. So just like this last problem, your displacement is up. Your displacement vector is up, and your force due to your muscles is upwards, correct? So that means you are doing positive work. Here's the weird part. The Earth, the force of the Earth, is actually you're taking, the work that you are doing is taking energy away from the Earth, right? There's a yin and yang here. When you do a pull-up, in both cases, you're pulling yourself up. The displacement vector is upwards, right? But the Earth is pulling you down, and this is the force of gravity of the Earth, right? In that case, when you're doing a pull-up and moving upwards, that's going to be positive work. Well, then you are going to be taking energy away from the Earth to do this pull-up, right? However, when you get to the top, well, now you're moving down, and your displacement vector is down. So when you are then moving down, the Earth's force is in the same direction as your displacement vector, right? Okay. And so now the work, the Earth is doing positive work. Again, that would be delta U sub g. Okay. And that is the reason why when we're talking about the work of the Earth, and this is negative, work is negative delta U sub g, when we're talking about the work of the Earth, that's the reason why we have a negative there, right? So this is where work is actually can be positive and negative. And it's why. It all has to do with the direction of the force vector and direction of the displacement vector. Think about it in another way. Another way to say that is if you are speeding up an object, you're doing positive work. If you're slowing down an object, that's doing negative work, right? Okay. So in both those cases, the displacement vector, if you're speeding up the object, the displacement vector is in the same direction as the force vector, right? So that means you're going to be speeding up. When your displacement vector is opposite your force vector, you would be slowing down. You could be said to be slowing down when we're talking about speeding up and slowing down related to this. This discussion, however, is related to delta U sub G. Okay. All right. Well, what I want you to do is go ahead and move on to your sapling homework. And if you haven't started it, please begin it. Okay. There are 3 homework problems related to this.